Hello, welcome back to the Cognitive Classroom. Today we're talking about variograms, and I thought we would spend the time explaining exactly how a variogram is acquired, how we generate its experimental data, and what it really means for you as a geoscientist. So let's start off quickly by explaining how we gather our experimental variogram data. We really use a variogram, in the modern sense, we use it in all three directions. So we're going to use a vertical diagram, and we're going to also use a horizontal diagram. So you can think of this one as a map against X and Y, or latitude and longitude, and this one here can be our depth direction. When we're looking at a typical routine that we get on modern packages, we'll often look at the vertical variogram as one well at a time. So you may see a visualization that gives you something that looks like a curve like that for an individual well. So that's something that we can use for variography. And in the horizontal direction, we'll have a fairly simple map usually. We don't bother necessarily showing you all of the normal beauty of a geological map, but just the individual well locations, and we could imagine these as a few well names across through here, A, B, C, D, E, and so on. Now, when we're calculating an experimental variogram, what we're going to try to do is understand if there's any mathematical structure in the spatial distribution of your data sets. And that's really its primary purpose. So what we want to do is have an analysis of this information and see, do we see, for example, a particular way that the data set is varying in terms of its random distributions. So in the horizontal direction, let's say we want to try to gather evidence of, is there a trend in the way that the randomness is occurring in a particular direction. We'll of course take the orthogonal to that trend later on as well. So there will be two directions that we're going to acquire. And we want to try to analyze to see, do we see a spatial pattern in it. In the vertical direction, it's going to come down the wellbore. Oftentimes you'll see some packages will give you the option of orientating the direction in the vertical. Usually I don't recommend worrying too much about this. Keep it vertical because each of the individual wells have got different dips as well. So it can be slightly misleading, that visualization. So what we want to do is calculate the difference between our pairs, and we're going to collate those as a function against its distance. So a distance in this direction, so here's our distance here, S, and this is going to be our third major direction at this point in time. So along this distance S, we want to see, do we observe any particular pattern in the way these data are being distributed. You'll see that we don't observe any pairs in that particular straight line from this measurement of well A. So in the real world, what we do is we create a binning tool to try to acquire measurements that we can say are indicative of that direction, but not perfectly in that direction. We'll define a tolerance angle, theta, that comes through here. And that should be less than 45 degrees because the other data belongs in the other direction. And a lot of authors will actually recommend that you do less than 22.5 degrees so that you've really got confidence that it relates to that particular direction. We often though have a limit on the on the lateral movement that we're willing to go, because we don't want to borrow data that's from too far away, even if it's within the tolerance angle. This is the bandwidth of the data set. And then finally, we want to try to create a statistical set from all of this. So we need to be able to make more than one pair land in a particular bin. So what we use is a thing called a lag, and that is a radial representation within that distance through here, and any two pairs that occur within those lags will get recognized as being equal. So let's have a look at how we can go about doing it. So we're going to represent this as these lags. So here's our lag distance, which is from here to here, from those two radii. And then we've got 1, 2, 3, 4 lags. We could continue that onwards, and that would make the range that we are investigating greater. Or we could create finer degrees of bins as well. We'll come back to choosing our binning in a moment. So let's have a look. In the first direction in this space, along this area here, within that first lag, we don't observe another pair. But we do at the second lag through here. So I start to create a column through here, we have lag 1, 2, 3, 4, 5, and so on. A does not have a pair within the first lag distance, but it does have a pair at the second lag distance, so I can make that calculation. And then what we're going to do is calculate the semivariance. Semivariance is pretty simple to calculate. It's going to be A minus B, and we're actually going to take the square of that, which is going to remove any negative sign, and that's the semivariance between those 2 points. And so we take that measurement for here. Now A can generate some other pairs for us. It can generate A to C, and that's going to occur in the third lag, so I can make this value here, A minus C squared. You'll notice that because we're doing minus and then squaring, it doesn't matter which direction it's going. So the variogram only needs to be calculated in one direction. The other direction is implicitly calculated here as C minus A squared would give the same answer. In this bin though, we also get A to D, so we can take A minus D, we can square that factor through there, and at the fourth bin we have A minus E, and we square that one as well. So there we go, we've got, from A we've been able to generate a total of 4 pairs in that particular direction. So this lag tool here that we've got is then reapplied at all of the locations across through here. And as we move that to, say, B, we would notice that B to D will turn into the, I'm guessing, about the second lag distance. So we could say B minus D squared occurs here, and B minus C might be over here, squared, and so on. And then that will probably fall into our third, let's say that falls into this B minus E, and then we can square that. Might not strictly be very accurate there, but just mental arithmetic as I'm trying to accumulate it. So what are we doing? We're starting to accumulate some semivariances at a whole bunch of locations. We're going to apply that all the way across the field. So this object here, this blue object that I've drawn, does not actually have a spatial position. It just has an orientation and a definition of its band, of its lag areas that it's going to acquire. It's going to operate all the way across the map. And it's also going to be able to go through the well system. So what we're going to do, through the vertical section, so it's going to generate a whole bunch of values along through here. We tend to observe when we do this in the horizontal directions that we might get next to nothing occurring in the first lag. We might get something at the second lag. You might find that you start getting a lot of different calculations occurring that tend to pop up at fairly regular lag distances. So you'll see spikes like this. That's your well spacing. Even on the offshore, but certainly onshore, we tend to find that we've drilled our wells at roughly the same spacing because we've obviously got similar drainage points between the wells, and so we often have these spikes. Once this has been inquired entirely, we're going to do an equation. We're going to take the average of all of these results here. So we're going to calculate the average variance, or semivariance here. And we can do that because you can average variances. And this is the reason why we use variance, not standard deviation, in this calculation. We can do that averaging. We're also going to record the number of pairs, the count. And the reason why we record the number of pairs is that we want to recognize what's statistically significant, because you'll see in this particular orientation, I really don't have a statistical sample here. The averages of one number, if I even achieve that, are not really going to be very useful. So commonly in the horizontal direction, you'll all be recognizing we end up with horrible numbers of pairs, very small numbers, big gaps, and really large areas that we're binning together within a typical oil field. So in the horizontal space, we very rarely get a good quality variogram. The vertical is quite different. You will see some programs will provide you with the same binning tool. You'll even be able to rotate its orientation against the well bore. And if you select the well name, you might notice that it will rotate. If you select a different well, it might suddenly rotate in another direction, so it can get quite confusing. You might start trying to orientate this thing in order to match one of the wells, but be aware that it's just a often unmarked direction actually as to where you're looking. So I recommend just keeping it vertically. And in essence for gridding, because we're working within IJ columns, you really don't need to worry about this too much. A couple of notes on the binning sizes. I don't worry about the log sampling. People often tell me that my logs have a resolution of 2 samples per foot. The reality, of course, is you have often log sampling at 2 samples per foot, but the resolution of the measurement can be very different. So resistivity can be much coarser if it's on the deep resistivity. Same with sonic, you might have a much finer quality spectral gamma ray resolution, but the sampling rate is not its resolution. However, what we're trying to achieve through here is we're trying to pick up the major changes that are occurring within the system. So we want the bins to be representing the frequency, those cyclicities that are occurring within that, and we're trying to avoid any aliasing that can develop by having incorrect binning sampling. The other thing is that we do the transformation, this variogram transformation is actually usually done on the normalized data set. So if we're viewing it like this, what we would normally have done, we would have come through here and we would have noticed this is fine, coarsening upwards in this case, if this was say porosity. And so an experienced interpreter might remove a pattern and say that, well, that's not random. So we can take that out of the data set. And then instead of viewing the raw data, we would be viewing that transform data. But even after we've removed that pattern, we're going to do another transformation. And we're going to do that for the purposes of making our mathematical trickery simpler. What we're going to do is what we call a Z-score transformation, or a Z-score for the Americans. We're going to take, to calculate the Z-score value for any observation, we are going to take its value, x, we will subtract the mean of the data set, which we're going to denote like so, and then we're going to divide it by its standard deviation. So why do we do this? If I run it through that transformation, or if I use a more elegant, say, quantile transformation, what's going to happen in the end, because I'm basically dividing its standard deviation by itself, my standard deviation for the Z-score in the Z space is going to always equal 1. Why is that useful? Well, we refer to standard deviation, so we refer to variance as that squared, because variance is simply the square of the standard deviation. So this value that we've calculated through here, the average over here, that variance, is actually also equal to 1 after we've transformed it through here. Now that's the reason why your variogram goes to a CIL of 1, simply because you've transformed it into this space. Right. The interesting point to note, of course, I've taken out this trend through here. So if I take away this trend and I remove that from the data set, I now no longer have the original observation. It's going to be the phi data, if this was porosity, given my depth trend. So it's actually a transformed data set. It's also going to have a residual that's plus and minus around 0, because these data would be positive, these data would be negative relative to that line. And so we'll find that minus its mean is going to be minus 0. We're going to end up with a distribution that has a mean of 0 and a standard deviation and a variance of 1. Now, we like variance for doing this computation because we are allowed to collate them together and average them. We can't do that with standard deviations, but we can transform it back once we've calculated it. You take the square root of your variance through here and you end up with your standard deviation. The other thing is, if we don't do it on the Z-score transform data set, if we actually do it on its natural coordinates, then the CIL is no longer a variance of 1, it's a standard deviation of your data set, which is a nice little trick for me, personally anyway, helps me understand what my variogram is doing. So let's draw out our variogram. Here is our typical variogram display. We have an axis through here with a distance s, that was this direction through here. On this axis we usually show gamma, which is the semivariance. It could also be denoted as sigma squared. Or if you do it in the way I like to do it, you could actually take the square root of that and just show it as standard deviation. If we were working in the traditional format that you probably know and loathe, that would go to a CIL of 1. If you've done it in the way I like to show it, in its natural format, this will be the standard deviation of your data set. So let's take our data set. Let's just say we've got this input data set here, porosity, I'm going to cause myself problems, I think. And we've got a data set that looks like this. We have a mean here, let's say, it doesn't matter what the mean is in this particular case, and we've got a standard deviation through here, and we kind of recognize this particular data set because we look at that data set all the time. So the standard deviation that I see through here, let's say that's about, I don't know, 4 porosity units. That's familiar to me. And that would be what my sill is going to trend towards in the end. We'll come back to how we're going to get there in a moment. Right, so we've got our plot up through here. There's one axis that's missing on our plot, and it's usually on the right side over through here, and this will be the count of the pairs. And we show that because some data are more significant than others. So at our first bin, we'll often see a histogram that looks like this. Second one might be a little bit better. The third one might be, I don't know why it always seems to be, the third one seems to have some information. And I might go back into a low again as I get to my well spacing, and then at distance I might see another spike up through here, and then perhaps as I go beyond that distance, the sort of subtle differences in between start averaging out, and I might get a subtly better pair over through here. So we show that histogram. Why? Why do we show the histogram? Well, when we plot these average values through here, we are going to see how much of these we need to care about. So let's say we've got something that looks like this. Right, what does that mean? So as an experienced interpreter, I will come to this and I will first off throw a degree of skepticism across this model. I'm going to look at this and recognize I've got very little data here. And I've also got less data here than I do on either side of it. I expect my variance to get up to my sill. So if you're in the standard space, you're expecting it to go to 1 if it gets to a stationary state. Or in this case, in standard deviation, I'm expecting it to achieve its standard deviation. That just means that at a great distance, an observational point tells me nothing more than I'm inside my own data set. That's it. So I've got no structural information, I've got no spatial correlation, but close by, we're inferring, hopefully, that the observation is going to tell me something about its adjacent point. And if it does that, that's a powerful piece of information for us to use. Now, we can't just use the experimental variogram data in a real modeling application, because when we do a simulation, we're going to need a value for this variation at every point for S. So we're going to have to infer this with a model. And we're going to use any continuous function, actually, to describe this. It is perfectly legitimate for me to use any continuous function. There is no reason for it to be exponential, Gaussian, and spherical. Those just happen to be 3 of the common ones. People might often look at this and say, well, I can see some cyclicity. Could I honour that? Well, actually, we can. You can honour some cyclicity in variography. You can do that using a whole variogram. So a whole variogram has some cycles to it, not saying that's a particularly good match. We often refer to it as, we often use a dampened whole effect variogram if we're going to use that. So it's a sinusoidal function, and the degree of sinusoidal behaviour is depreciating over time. That's the dampening of the dampened whole effect variogram. What does that mean to me? Well, it means that at some distance, as I get further away, I start to see a similar behaviour to this observation again. That's actually quite a reasonably common situation in geology. That's when we've got some regional scale or some larger scale features, like some large dune system perhaps, or some parasequence behaviours that were occurring in the vertical direction. So we get progressively more dissimilar, and then it starts to become more similar to that observational point again. The dampening is because over distance, the thicknesses of those cycles isn't perfect, and so the sampling rate starts to add positive and negative relationships together, and it eventually sorts itself out. The whole effect variogram, though, isn't commonly used, partly because it's not available in a lot of the packages. Some people find it quite difficult to understand. If you put yourself back into understanding, talking about what it's inferring, to say that this tells me something about sort of the frequency or the wavelength of my events in the geology, it's actually not too hard to understand, to be honest. But we often end up using something a little bit simpler. Now, how would I come about weighting it? Well, I'm going to look at this observation here and say there's not a lot of statistical information, so I could actually ignore that value if I want to, or at least not honour it. In reality, it's got a lot of potential error associated with it. Likewise with this one, there's still some error with that. This piece here starts to have less error because I'm saying I've got, I'm calling it more statistically significant. So realistically, we could think about our variograms as something like this. We need to make a model that fits through those lines, through those error bars. And so I could come up and do something that ties through those. Well, that's a pretty terrible one, but let's say that's a roughly spherical example. So we've got a model through here, or maybe exponential, that we're going to plot through them. So what are the elements of the model that matter? We need to know the model name. So the model that we're fitting here, and let's say this is, let's call it spherical. Say this is a spherical model, so that tells the computer immediately how that function is going to get defined. I need to know its nugget, and I need to know its range. And I actually don't need to know its sill. The sill is actually going to get used in most simulations. It just comes from the data set. It's not actually taken from the variogram during the execution. Right, so a couple of points. Nugget, if you don't recognize it, it comes from the gold industry where all this technology was developed in South Africa back in the day, and it reflects that instantaneous change that can occur between two data points, and that's at the immediate change point. Now, a lot of companies, and including the one that I first learned this methodology with, have a rule of thumb that say that we must always have a low nugget. In fact, one of the companies I worked for had a mandate that the nugget was always 0. And why? It took me a long time to find out why we did that. And because it's not obvious. The reality is not to do with geology. There are plenty of publications out there that make that claim, that it's to do with geology, because the 2 points between observations are often similar, but that's not the real truth. The reality is because we do a simulation simplification. When we take 2 cells into a dynamic flow simulation model, we are going to make a calculation to determine how much fluid flows from one side to another given a certain amount of time. And we make that time step quite large because we're trying to save on computational cost. It should be a T. Computational cost. We want to have a large time step in between these wells in order to minimize the amount of time it's going to take to compute. And the problem is, if this cell here wants to try to send 100 barrels across to that cell in that one time step, but this one can only receive 50 barrels, we're going to have to find somewhere else to send those other 50 barrels, or I'm going to have to increment on my time step. So this becomes a convergence problem in flow simulation. That is entirely because of a computational simplification. It's got nothing to do with geology. And so anyone that tells you that the nuggets is always low in geology because the things are similar, they need to recognize that there is also a component in the way we have that rule of thumb that relates back to this flow simulation. Part of the problem with this assumption of low nugget is because most people are doing a Z-score transformation. We're dividing it by the standard deviation. Now, if I take out a trend out of the data set, my original standard deviation was 4 porosity units. I take that trend out, I might be able to reduce that standard deviation down to 0.02. You'll note that I've really not done anything to change the instantaneous variation between, or very little. The main change is actually occurring over a greater distance. So the nugget is referring to the changes occurring over a very short distance. So it shouldn't have changed, but because I'm now dividing it, instead of dividing it by 0.04, I'm dividing it by a smaller number, my nugget will seem to climb, and my sill is already being forced back to a value of 1. So if I take the trend out, it would mean that the nugget would appear to climb, and so it looks like we're breaking this rule of thumb, but the actual reality is not going to break it. So it's okay if that nugget climbs up if you're working in Z-score space, if you're taking your trends out. That's just what's going to happen because your distribution set is going to get progressively narrower. So this is just a rough summary of what we do in variography. When we come to applying the variogram in the property simulation space, what we're going to be using is a representation to say that if I have a grid cell, I've got my model through here, or a quick model up, and we're saying, okay, I've got some observation points, I've got some unknown points. If I'm trying to make a guess, if I've got an observation in this cell, so a well sample through here, if I come to guess what's in the cell next to it, okay, I can come along to this and say that, well, that observation is within distance, so I need to be within this much variation of that observation. So that's how we get to preserve some of the spatial structure. Once we get beyond the range, we come to make a question mark over through here. That's not going to give us any information. So that's how we're going to use the variogram later on. There are lots of different methodologies, both for continuous and continuous and discrete properties that we can use variograms for. But I hope you can see that this is just a potential way of describing the mathematical structure that might exist inside your data sets. It's one that we use in the industry because it's nice and easy to acquire, particularly in systems with pretty poor amounts of information. But it's not the best, it's not the only. It's just one form of a branch of spatial mathematics that is used and has become popular in our industry, in part to do with some reasons for flow simulation calculations. It's useful in that, and it also helps us trying to describe the structures in our data. But in my personal experience, I do prefer to focus on trying to understand the geological structures and link that back to geology rather than just focusing on the variogram. But nonetheless, this is how you calculate a variogram. I hope you found this useful. If you've got any questions and you'd like to bring up some other points, please make some comments below. But otherwise, I'll see you back here at the Cognitive Classroom next time.